Here we see three states of the system, which we'll identify as State 1, State 2, and State 3. State 1 is characterized by the fact that we're at atmospheric pressure, original volume 2,000 milliliters, and temperature, room temperature 297 Kelvin, just the state of the system before we do anything to it. State 2 is the state of the system when the water is at height h, the maximum height, the height of the reservoir. State 3 is the state of the system when the temperature reaches its maximum possible temperature, in this case 353 Kelvin. State 1, we see the pressure, atmospheric, volume, and temperature. State 2, we don't know the pressure, we don't know the temperature, we do know the height, and the volume is remaining constant. And from the height, then, we're going to be able to determine the pressure. Then from the pressure ratio and the original temperature, we can determine the temperature. State 3, we're 353 Kelvin, our assumed high temperature. If we had a different high temperature, we could find the corresponding results for that temperature. Pressure is going to be the same as it was here, P2, whatever pressure is required to hold the water at altitude h. And really, I guess I should have drawn this tube still being full of water. And this will be our State 3. So State 1, State 2, State 3. Now what we asked people in class to do was to determine the various unknown quantities, that is, the pressure at State 2 and the volume at State 3, and therefore the change in volume, and finally the change in the potential energy of the system for different values of h. Again, outlining the process, Bernoulli's equation is going to be what we use to find P2, the pressure after we've raised the water up to the height h. From P2 we find T2 because V and N remain constants. The pressure and temperature are just directly proportional. We know the temperature T1, the original temperature, so we can easily find temperature T2 if we know pressure P2. Then, for State 3, knowing the temperature in State 3 and the volume and temperature in State 2, and the fact that the pressure remains constant up to State 3, we can easily determine volume V3 by simple proportionality again. Then we determine the change of volume. From the change of volume, we can determine how much water is raised. Then we can easily, from the height, determine how much potential energy the water gained. And we did this in class using altitudes of, I think, 0.1, 0.3, 0.5, 0.7, and 1.1 meters. Just to show again the use of Bernoulli's equation, figuring the pressure at State 2, if we have points A and B, and I really should show a picture here. If we come back here, okay, State A, I think, is the state down here at the water surface. State B is the state up here at the open end of the tube, at the where the water surface meets the air. So we have State A, or point A, and point B. I think state is the wrong thing to have used here. Actually, I didn't use state with A and B. Okay. In State 2, again, where A is the point at the surface of the water in the bottle, and B is the point at the maximum height. The velocities are all zero, so we have zeros here. The altitude of the water in the bottle we're going to take to be zero. In other words, we're going to take the water surface in the bottle to be our reference point for altitude, so that the height at B, being h units higher, will be h. After we get rid of the three terms that are zero, we see that the pressure at A is just rho GH plus the pressure at B, which is 1 atmosphere, B being the pressure where the water meets the air at the top of the tube. Okay? And that's familiar. We've seen that. So that might help. You should go ahead, if you're doing this at home, and calculate the potential energy gains for different heights h, from 0.1 to 1.1 meters, going by odd tenths, that is 0.1, 0.3, 0.5, 0.7, 0.9, and 1.1. Okay, if you do that, you should stop your video and go ahead and do it. But we get these delta V's, okay, these changes in volume. And from these changes in volume, remember this will be in milliliters, so the change in volume is equal to the number of grams of water raised. So from the number of grams of water raised and from the height, we can easily determine the potential energy change. And what we see is that at a height of 0.1 meters, of course, we don't get much increase in potential energy because 0.1 meters isn't very high. Even though we pump a lot of water, we don't pump it very high, so we don't get a lot of potential energy change. Actually, at 0.9 meters, we get our maximum potential energy gain, at least the maximum from among these heights. At 1.1 meters, we get less potential energy gain than we did at 0.9 meters. Now, that's because we didn't pump as much water. We didn't pump enough water to make up, we didn't pump much water, and the difference in height didn't make up for the loss of the volume of water or the weight of water raised, and we ended up with a less potential energy. So we see if we graph the change in potential energy versus the height to which we choose to raise the water, the graph will go up fairly rapidly, it'll peak, and then it'll start coming down. Remember that at 1.5 meters, we're going to have no water raised. 1.5 meters is as high as we can raise it. We'll be at our maximum temperature at 1.5 meter height and won't have any more thermal energy to add to the system to expand the water, the air, and therefore displace water. So we're going to get zero volume at 1.5 meter height, and we'll be back down to zero. So the curve goes up, comes up here, and then comes down quite rapidly.